but we can go all the way in to almost the native resolution of 30 meters of these images, and then it starts looking, well, some of them is quite steep in there. It's probably above 45 degrees, so let's go all the way up to like 60 degrees. All right. And then once again, if you want to check what the steepest stuff is, you can use your inspector to click on different areas. Okay, this one says it's up to 74 degrees. You know, it's still a representation of the slope from a discretized unit, so you might have some vertical cliffs in there too that it's never going to quite capture. But overall, what we wanted to see here is the ability to calculate a image. So this, in a sense, it's a computed image that's called slope that we can add as an Earth Engine object, once again, as another layer, and display that. And it's pretty quick to calculate. Like if you actually start panning over to the side and zooming in, it's hard to tell that it's being computed on the fly for the most part. Actually, it's hard to tell which one I'm at, so let me turn off the other ones. This one's slope. That as you pan to the side, it's like as fast as I can pan with a quick internet connection, it can calculate things like slope. There are other operations when you start getting more and more complicated where it may take a few seconds or so or longer to come back. But for a lot of things, you can do them on the fly, and it's just as if you had a stored image that you're accessing. You don't actually know that you're generating it on the fly. Okay, any questions on that? That is our script number 03 over there on the side. Is just showing that we can do a computation on the fly. Yes?
I want to know more about how I define min and max. I don't know if it's
Okay.
like related to the data or
It is very much still related to the data, yes. So let's look back over the few layers that I did define a min and max for right here. The first one is an elevation layer where the data is in units of meters. So I just picked something that I thought was reasonable for the United States, 0 to 1,000 meters, which probably wasn't high enough. So I had increased it at one point to 3,000 meters. But that was more just knowledge of, you know, what the variation in elevation is in the region of the world I'm looking at. Similarly with slope, it's between 0 and 90 degrees, the output of this function. But there's probably not that many things that are like really steep slopes, so I picked something that was lower down. And then finally for this one, occurrence, I picked 0 to 100 because of looking at the metadata for the occurrence band. It goes from 0 to 100. I basically had to look that up to figure out whether I should do it between 0 and 1 or 0 and 10,000. Depends on how they scaled the data. And in this case, they've scaled it to be between 0 and 100. The other way, if you don't have any intuition about what it should be, there's still other ways to do this. Let me get out of there. Okay. There are some other ways to go about figuring out what the min and max could be. If I bring up the layers panel there and I go over one layer, maybe I'll do the slope one in this case, and hit the gear icon, it brings up a dialog box that helps you to figure out what the visualization parameter should be. And in this case, it's saying I have a custom range right now of 0 to 60 degrees for a range, but maybe I want to capture 98% of the values or something like that. And I can hit stretch in there, and it went and calculated what the range should be if I wanted to capture 98% of the values. And there's a bunch of different stretches that are within there. So you can use this to get an idea of what the range is just based on what you're seeing on the screen or what is being displayed on the map.
so this min and max is can be different things.
The min and max,
Meters.
yeah. So it's in the units of the data. So in this case, the units are different. The first one was in units of meters. The second one is units of degrees. The third one is in units of percentage, or I don't know if that's quite percentage. It's from 0 to 100, basically. Percentage value is from 0 to 100.
Thank you.
Yep. Cool. You had a question behind him? Yep. Okay, cool. All right. Then I will embark on the next one. All right, the next thing that we are going to do is define a spatial reducer. So often it's interesting to know like what is the average property or min-max, etc. Different properties for a region in space. So we have some drawing tools that are available in the code editor that allow us to define like polygons here. So I'm going to click on the polygon looking tool there in the upper left, the geometry tools, and it created a new object called geometry that appears in my imports at the top, and I'm now in a drawing mode for being able to click on the screen and say, hey, I'm interested in that polygon right there. And after I'm done and happy with that, I can hit exit. If I want to move that polygon around, I can click on it and drag it to move it somewhere else, etc. I can modify vertices, etc. You can kind of manipulate the geometries. But what's important about this is I now have a variable called geometry that I can use to summarize different pieces of information. So given that we are a little bit behind, I'm not going to do this typing, which is quite a few things. I'm going to click on 04, apply a spatial reducer, and say, okay, replace the script. And we're going to jump and see basically what I would have typed out if I had more time. And I have two commands here. The one is the statistics for summarizing slope. So if I go through here, I have the slope image. I'm going to reduce for a given region. There's a method called reduce region, which means it's going to take a spatial region, apply a reducer, like a way to reduce all the information in that spatial region. The reducer I'm going to use is called mean, so it's going to get the mean value within that polygon. I have to specify which region I want to use, and it's my variable called geometry. And then you also get to specify the scale that it is applied at. So if you're doing this for the entire, like an entire nation, continent, etc., don't do it at 30 meters. It'll take a long time. But you basically can, there's some other parameters that allow you to do approximations when you're looking at large scales like that. So you don't actually have to go down to the full 30 meters. But in this case, I'm saying, hey, run it at 30 meters specifically. And then print out the end result. So if I run this and then look over in my console tab, which now has lit up because it has some new information there, click on the console tab, there is an output called slope dictionary there, slope dict, and inside it there is a dictionary that has a single property called slope, which is the mean value of slope in that polygon. So for what I did right there, the mean value is 25 degrees. To just check out to see how this is working, I'm going to drag it up onto the plateau, which is the flat part of the Grand Canyon. Say exit, run it again. And now my slope should be, yeah, slope is now 2 degrees or something up in there. So it's basically just summarizing whatever information is in that polygon. So that's, any questions on that first one? Sure. Yeah, the scale here is assumed to be in units of meters. So it is, there's a little bit of, the original data might have been in degrees, but we are specifying the scale to reduce that in terms of meters. And in order to do that conversion, it's going to figure out what is the nominal scale in meters of that unit of measure at the equator. So it's basically approximately 30 meters at that point, but it changes as you go different parts of the globe. Yep. That's a good question, though, because the scale parameter appears in many of our different methods, and normally it means that if this was, it's the nominal scale at the equator for that projection. All right, the second one example that I wanted to have here is sort of along the same lines. but it's going to do a little bit more of a complex operation involving water here. So we're going to take our water image, that JRC surface water occurrence. We're going to select out a particular data set called occurrence, and then we're going to look for areas where the occurrence is greater than 90. So that means it's water most of the time, more than 90% of the time in the record. We're then going to take that and multiply it by this image that is called pixel area. So I'm basically going to take all of the areas that are more than 90% of the time water and multiply it by what is the area of that pixel. And then I'm going to run a reduction over that sums up all of the areas. So in this way, we're sort of like counting the area of water, multiple steps. And I'm going to run I ran this already. If I go over and look at my water dict output, occurrence is 0. So that means there was no water pixels in my polygon, which sort of makes sense. I mean, I'm highlighting an area on the plateau where nothing is blue. But just to check that this works, once again, let's move that to somewhere over the bottom of the Grand Canyon. And I'll run it again. And then I'll expand out water occurrence. And now in the area that I highlighted, there is 46,000 square meters of water, according to those data sets. So this is very useful whenever you're doing like a classification, like what is a certain land cover type and you want to know how much is there. You can do this type of operation where you multiply by the area of the pixels and then reduce to sum up all of the values in there. This, don't worry if you don't understand the details of that, because we have a much more detailed explanation in our documentation if you're interested in this pixel area function and how you utilize it correctly. But I just wanted to give you a little bit more of an example of a more complex reduction where you're counting up areas, because it's a very common thing that people often want to do. Yes? Yes, and so it changes as you zoom in and zoom out, and it also changes as you go to the poles. But at the level of building an algorithm off of it, it's basically going to say, regardless of what resolution you're reducing at, pick the appropriate pixels area for each pixel. Yeah.
The order of the functions is important in this way. Like I can put select in front of gradient and or
Yep.
reduce.
So sometimes it's important, sometimes it's not. So if we start from the top, and I'm going to break this onto multiple lines here. So that's one of the things I actually do like nicely about JavaScript, is that you can break things into multiple lines without worrying about the syntax. But we start off with water, which has multiple bands. And then I'm going to pull out a single band called occurrence. And then I'm going to check whether it's greater than 90 meters. I could have done that in the opposite way. I could have said, hey, for all of the layers of water, figure out which ones are greater than 90. But it's not going to make sense potentially for a lot of the bands, but it doesn't matter, because my next line is I'm only focusing on occurrence. So in this case, it should give me exactly the same results if I did the opposite order. That being said, a lot of times that type of commutative property is not true, depending on what order you do these operations. For example, I would not want to multiply by pixel area before I tested to whether it's greater than 90, because that's going to distort things tremendously. So in that case, the order is very important. And you can think of it as that I start with an object, water, and then the next line when I do dot some method, I'm applying that method, and then for the results, I'm applying the next method, etc. So it's sort of like you're chaining them all together. And I could have broken this out into multiple lines of JavaScript too. But many times you're trying to chain together a lot of things together. So it's useful to write them in this syntax.
Okay.
Cool.
So the sequence of processing these functions is from the outside in, and you put it in line. So they start from the most out function is inside brackets.
The way I would think of it is that you have a image that you are applying operations to. And so in that case, I'm starting from the top and moving to the bottom, or if I put it all in the same line, starting from the left and moving to the right. So I'm starting with the water image. I'm selecting a band, and then for that single band, I'm testing it against a threshold, 90. Greater than 90 is what this is short for. I didn't explain that before. And then multiplying it by another image. So it is sort of left to right or top to bottom, depending on how you have formatted your code. Cool. All right. So it was basically those two statements were basically calculating dictionaries, calling reduce region, which is reducing a spatial region, and it produces a dictionary of objects, keys that we can print out to the side. But that's one of the ways you can summarize a lot of data in space. There's other ways to summarize it in time, etc., other ways as well. But this is the spatial reduction for a spatial, or it's a reduction for a spatial region. All right. Any questions on that? A lot of blank stares there. Maybe it's the lull after the coffee break. All right. So let's go to. Woohoo, got to the second page. We're gonna sort of shift gears now too. We've sort of done. We're done right now with the single band images, and we're gonna move on to multi-band images in large collections. So we're gonna take a little bit of a leap. But before I do that, I just want to make sure people are clear of what we did with these simpler single images that have a single band, or reduced down to a single band. Okay, we're going ahead then. Go up to the top and say clear script. And we will start again. Yeah. Yeah, that's really daunting. Okay, if you don't want to do that, it's a little too late, but there is a save button up there if you want to save it into your... But since we're following along with this script, you can actually just, go back to any of the ones that I created before. All right, so we are now going to break into satellite data analysis. So I want you to look up Landsat, TOA, and the one I want you to hit is Landsat 8. So if it doesn't appear on your first list here, you can always hit return and it'll bring up a whole search list for a bunch of different rasters. Hello. Or it should at least. Now it's just thinking. All right, we're going to go back. Yeah, so USGS Landsat 8 Collection 1 Tier 1 TOA Reflectance. And I can try to parse that title out a bit, but let's import it first. And I'm going to call it L8, so capital L8, because my little L's get confused with other numbers in there. But yeah, let me try to explain what that means. So we have USGS, the provider, runs a Landsat program that's been going on for over 40 years. There is a platform in the Landsat program called Landsat 8, which has been flying for 5-ish years. I guess it's been... Okay. I don't remember exactly when it went out there. It's been about 5 years. They process this data, and they have come up now with what they have considered to be collection 1. Before, they used to ad hoc just keep improving their processing, but they realize that is kind of frustrating for users that are trying to figure out what the versioning is. So they now have declared this as collection 1, and eventually they'll get to collection 2 when they have a whole new processing flow. But collection 1 is a way that the USGS process their data to make a product. Tier 1 means that it was mostly cloud-free, and they were able to georeference it to the ground quite well. There's other tier 2 stuff where they weren't quite sure because of clouds or too much ocean is in the image, that they weren't be able to georeference it to similar quality. So that's tier 1. It's the high quality stuff. And then finally, TOA is top of atmosphere. So this is sort of what the reflectance appears to be at the top of the atmosphere, but it still has a bunch of atmospheric effects in there. Reflectance. So that's the whole title there. But you can think of it sort of as just Landsat data. Unless you want to get into all the details of that. But we do have a lot of Landsat collections, so it is important at some point to understand what all those mean so you can pick the right Landsat collection. All right, so let me go and done there. Okay. All right, so now we have one variable in our import section that is called L8. This is an image collection, so it is rather large. You don't have to do this, but I will do it for you. L8.size. And that will just go through and try to count up all of the images that are in that collection. But what we are going to want to do is actually go through and do some filtering. So I'm going to say this is my analysis section, and I'm going to say var filtered is the name of a new variable, and that's going to equal Landsat 8 dot filter date. There's a lot of different ways we can filter this Landsat collection. I'm going to do a special one that's just filtering by dates, and then we can specify the start and end dates. So do sort of whatever you want as long as there's data available. So probably within the last 5 years. And I am going to do May 1st, 2016, and I guess we'll try 2 weeks out on there, 2016 05-15. Okay, so what that is going to do is it's going to narrow down the amount of images in the collection because we're going to filter it by date. If you look over on the right hand side, in the console, I printed out the full size, which was 801,000 images currently in Landsat 8. And if I move this down below that print statement, I then could print out what filtered is, next variable, and it's going to be substantially less when I run that. It's going to come back faster too. So in that 14-day period from May 1st to May 15th, there was 6,412 images globally, because I'm not constraining it right now by any particular location. So just in that time range, that was how many was there. So not sure how many that is per day. Usually it's on the order of like 700 per day. All right, and then the next thing that I want to do is add to the map. So map, add, layer, filtered. And to start off with, we're gonna not do any visualization parameters. And we're just gonna make sure we get something to appear on the map. And if I zoom out far enough and move over to California, so I'm sure we're a little bit more aware where I'm looking, we at least have, some data appearing. It's overlapping data because we're doing 14 days, and that's pretty much when you get every 16 days you get a full repeat of the Landsat 8 sensor. If I made that something less, like maybe we do 1 day's worth of data from May 1st through May 2nd and run it, then you're going to see a bunch of stripes. And sometimes they haven't processed the data. Remember, this is tier 1, so they haven't, if they weren't able to georeference it, it will not appear in this collection. So I'm imagining whatever happened over Kansas and Nebraska on that day was it was really cloudy and they couldn't actually figure out how to georeference the images in there. But that's pretty much for a single day. All right, so what we've gone over right now is how to reference an image collection. This one had 800,000 images in it. Filter it down by time, and then add that to the map. It doesn't look like much on the map right now. It's just, you can see where the data occurs, but it's kind of strange looking. We're going to improve that next.
Is it possible to write a code here to set the spatial resolution?
To set the spatial resolution? You can reproject into a particular spatial resolution if you want to. Oh, you can also crop in space too. There's something called clip, is the way that you would clip out a boundary. Yep, so both those are possible in your code. Yep.
Are you going there?
No. Though I will show later we're going to export at a particular resolution for a particular geometry. So related to that, we're going to do later. But most of the time when you're working with data, you can apply these methods everywhere the data occurs, and it doesn't slow down your processing. So usually when you want to clip or set a particular projection, it's the very last step that you will want to do. Because if it's not slowing it down, might as well do it in the full projection. And in the case of a lot of the stuff in Earth Engine, when you try setting the projection explicitly, it will slow things down. Because if I said I wanted to now look at this at a 30-meter resolution, said reproject at 30 meters, it's going to have to load all of those 30-meter pixels together to show you a representation that you can't even see the 30-meter pixels. So it will slow things down dramatically. So you can do that, but I'm going to say most of the time you don't want to do that unless there is unless you have a real reason that you do want to force it to a resolution. Don't.
How about the radiometric corrections?
The radiometric corrections, generally they are done to the data before we bring it into Earth Engine. So this is TOA, top of atmosphere. There is also a surface reflectance product that Landsat puts out. So is that the correction that you were talking about?
Yeah, I see a lot of clouds here. So
Oh, yeah. So this is top of atmosphere collection. They haven't tried to do it's the raw data before you've done any type of cloud masking within it. I would say a lot of times getting the initial data into Earth Engine is the stuff that's super fast, and then dealing with all the noise is the stuff that takes you a long time to deal with, because there's so many ways to try to detect clouds, shadows, etc. And it depends on how much data you have, what approaches you're going to take. So that it is possible to do that in there, but there's not one unique way to deal with the clouds and shadows. Okay, so let's go back and pick some visualization parameters for this to make it look nice. Once again, I'm going to break this into a couple of lines just to make it easier for everybody to read. And I'll make that even a little larger. So we're going to take our filtered data set and let's specify some visualization parameters. I am going to say, once again, there's a min and max. Min of 0, max of 0.3. The question is going to be, how did you guess that? Well, I know that top of atmosphere reflectance of Landsat goes between 0 and 1. Reflectance values are from 0 to 100%. So most things are not really all that reflective on Earth. They tend to be in the lower range of reflectance. So that's how I picked 0 or 0.3. But once again, you can inspect around if you wanted to actually figure out what the real values were within there. I also have to specify which bands I want to display. And the way to do that is use a visualization parameter called bands. And there's a few ways to specify it, but I'm going to specify a list of the bands. Take a little diversion up here and go back and review the band names here. That the names of these bands are like B1, B2, B3, B4, band 1, band 2, etc. The ones that I'm most interested in are band 2, 3, and 4, blue, green, and red, and band 5, which is near infrared. So that's where I'm getting the naming convention from of which B's I'm going to display. But I'm going to say B4, which is red, B3, and B2. So those are the three bands I'm going to pull out. That's the red, green, and blue bands. And I'm going to put those into a visualization where it maps to the red, green, and blue channels. So it should look sort of like what you would see out if you're looking out of an airplane. And I'm going to run that. And I'll zoom back into, I guess we're not in the Bay Area, we're somewhere on the coast. And it's looking pretty reasonable. You can see clouds there. As I go over on this side, you can see what looks to be agricultural fields, which are grays and greens, etc. A little bit hard to see, I guess, with the lighting I have there. If I wanted it to be even brighter, I could do something like 0 to 0.2 is the maximum. And then it's just going to look a little bit brighter on our screen up there. But we can think of this as sort of a true color, at least close to true color representation that Landsat is seeing. So I'm going to actually call that true color. So any questions on that? We basically have taken 3 bands, band 4, band 3, band 2, that correspond to red, green, and blue, and mapped them to basically the screen in the red, green, and blue channels directly, so it looks like a true color representation of there. All right. I am then going to do an alternative representation by copying this entire set of map add layer and pasting it down below. And instead of band 4, 3, and 2, we're going to shift it up a notch and say band 5, which is the near infrared band, and then band 4, band 3. And that is what is often known as a false color representation.
Does the order of the bands matter? Like, is there a drawing preference?
Sorry, the order of these bands? Yes, it does. And I will experiment with that in a second. But what a false color representation does is it makes vegetation look really red. Clouds still look white, shadows still look like shadows, but things that is healthy vegetation appears quite red because it is a very reflective in the near infrared part of the spectrum. The near infrared values are very high, higher than the red, green, and blue values. All right, so just to answer that question about does the order matter? Yeah, I'm going to take band 2 here for our true color and move it to the beginning. Okay, so if I run this now and I have mapped, let me think if I can get this right, I have mapped green and blue. Anyway, I've mixed up basically the channels of the satellite to the channels of my display, and it looks kind of bizarre. That being said, sometimes this is kind of neat to do. If you can find particular combination of spectral channels from the Landsat sensor. If you map them to certain color channels, it makes properties stand out dramatically. And depending on the combination, the different properties stand out differently. So if you ever look at Landsat band combinations, I'm going to just search Google for that. There is a bunch of these on here. The one that I like, if I can find it on here, there's a USGS page right here. And they give a bunch of different examples of color infrared, false color. I guess they don't have that many in there. Some of these pages will give you a lot of different band combinations to tease out different features of there. So anyway, it does make a difference. For the purposes of this one, we're going to probably stick with things that look like the eye is expecting them to look. So we'll be back up to that. Okay, so band 4, band 3, band 2. That's our true color. And then our false color right there. Any questions on that? Alrighty. The next thing that we are then going to go over is, since we now have used a bit of the image visualizations for the bands, we're now going to do a little bit of reducing in time, in a sense. It's basically a stack of images that we want to reduce down. And so there's a couple of things I'm going to use just to clean up my code a bit. One is I'm going to use this visualization of true color quite often. So I'm going to copy this dictionary up to the top of my script so that I can keep reusing it. So I'm going to create a constant. I'm going to say var rgb _ viz. And that's just going to be this dictionary that I'm going to keep using over and over to display a true color representation. And then I don't really need to show the false color anymore. I'm going to clean up my code, so I'm going to have this all in one line. Okay, let's make sure I didn't screw anything up by running it again. Okay, so there is a true color representation there. And then the next thing that I'm going to want to do is, well, I'm going to expand it. Right now, we don't have the problem with overlapping scenes because I only had a single day. But let's make that so we are going to look at like maybe 3 months worth of data. So if I run this with a wider temporal filter, you're now going to have a bunch of overlapping data. And some places it looks coincidentally clear. In others, it looks kind of cloudy because it's just showing you what the last image on top looked like. So by default, when you have overlapping images in Earth Engine, it does what's known as a mosaic operation, which means whatever the last one was, display that. But often, if you're looking at something that changes over time, that might have clouds and shadows and stuff, you might want to do a different reduction, which would be something like a median. So, sorry, I don't want that in my visualization parameters. I want to back up one. So filtered.median. That is taking an image collection that's called filtered, and then it's applying a reducer across all the images called median. And if I run that, it's going to be a bit different here with the results. Sometimes it will look better, sometimes it will look worse, depending on what the last image was. But when you're starting to aggregate over a long period of time, generally reducing by a statistic that's going to pull out a value in the middle is going to help relative to having a mosaic reducer. All right, so one thing that we could do is compare the two. So the default is true color, and then I'll put this one as median down here. And we can run that. And I'm going to zoom into some area that we can hopefully see some differences. All right, so I am over now in an area that's it's not cloudy all that much. It's still like a high desert area, but I can now flicker in between, you know, this is what the median or the mosaic, like last on top image looks like. There's some clouds and shadows, but then if I compare it by turning on the median, those go away. This isn't going to work everywhere. I'm going to go to South America next where it's really cloudy, and you'll see how it doesn't work. But
Does the median function take the clouds out, or are they included in the median?
the median function does not directly take the clouds out, so this only works if the median value occurred when it was not cloudy. So assuming that you're looking at an area that is clear more than half the time, it's probably going to look pretty good. But for example, if I go to Guyana, see how it looks down there. That is our, well, this is the true color representation, and this is the median of the stack. Doesn't look that different because it's cloudy there often, so it's not the best approach for doing that. One that could be better for getting rid of clouds is take them in. So if I change my last one down there to do a minimum reducer, the minimum reducer does look better, but it only looks better to a certain extent. When you start zooming in closely, it's going to be all full of shadows. So it's not actually going to be a great representation of what's going on the surface either, especially when you go over long time periods. There is also more advanced percentile reducers. So if you have a large stack, you might say, I want the 20th percentile value of this entire stack. That can work kind of good sometimes. If you really are interested in clouds, you can do a max reducer, which generally looks like that. So it all depends on what your analysis is that you're interested in. But the main concept of this is that you can take a large stack of images and reduce them down. And for cloudy parts of the world, you might want to take a full year. Sometimes you have to do 2 years worth of data to get something that's sort of cloud-free. That's just the reality of trying to look at surface properties under cloudy conditions. There are other approaches where you will take an entire image collection and first try to remove all the clouds by some of the images will provide QA bands saying whether they think something is a cloud pixel or not. you could apply those first and then take a median later on. That can work under some circumstances. All of these sort of work under some circumstances. They always work great in like dry desert areas, and they don't work as good when you go to somewhere like Guyana.
Yeah, right.
All right, so anyway, any questions on that? Digression on a bunch of different reducers. It's a good approach if you have a lot of data and you're not looking for something that changes really rapidly. Okay, the next thing I want to do then is go into doing a calculation of NDVI, but in order to prepare for that, we're going to focus working on a single image, just so it's easier to understand, and then we'll come back out and apply it to all of the different images. But it's often easier to understand by working with a single image. So if I go back up to this part of the world, San Francisco area, and then I'm gonna drop down using my geometry tools once again. I'm gonna pick the one that looks like the little place mark, the second one over there, add a marker, and then I'm gonna just drop it somewhere in the San Francisco area. And so this variable is also by default named geometry, whether it's a polygon or a line or a point. We just call it geometry, and for I find it convenient actually to leave it there, just name geometry, because when you delete one and you add a new one, you don't have to keep renaming them. But for right now, we have a new variable called geometry here. And what we can do is add that to our little filtered area so that we can say filter bounds and then have that be geometry. And if I run that one, it now only returns images where the bounds of that image intersect with the geometry. So that's way to, we haven't isolated it down yet into a single image, but it's at least images that are all stacked on top of each other. The next thing that we can do to just get an image out is apply another method that works on image collections that's just called first. And in this case, it's going to pick out the first image of the collection itself. I'm actually going to separate that slightly into a different line. We're going to call a new variable called image, and that's going to equal filtered, which is our filtered image collection. And on the filtered image collection, I'm going to call first. And this method called first is kind of interesting that you can apply it to many different types of collections, and it doesn't necessarily know what's inside of the collection. So in order to educate it, I'm going to say wrap this with a call to ee.image, which basically says like whatever I've gotten back from first, make sure it's an image. And that way the rest of my code is going to know that it's an image object to work with. This is a confusion point quite often working with collections and trying to get images out of them, is that some parts of Earth Engine can't know exactly what is coming out of the collection until you tell it to. So we have to explicitly say this is an image. All right, and then at this point, I take and just display that image. Okay, so now we're down to having a single image. It looks sort of the same as before, but if you use the inspector tool and click on it, you will see that it's a object which is of image type. Okay, so that wasn't the most exciting way. It was just kind of setting us up for what we do with an image. And what we're going to do next is compute NDVI on that image. So working with that image object, we're going to extract out first the near infrared band. And to do that, we can say image.select the name of the band, which is near infrared, which is B5. And then the same for the red band. If you don't want to type this, that's okay, because I'm going to erase this in like 3 minutes. B4. So that's 2 bands that we've just pulled out, and then we can calculate another image, computed image called NDVI, and that is near infrared, subtract off the red, and then divide by the near infrared, adding the red. And hopefully I got all that right, but we will find out. And then down here I'm going to say map, add layer, NDVI. We're going to have to do some custom visualization parameters again in here. Who has taken a remote sensing course and played with NDVI before? Okay. The range, what is the lower value? Min's -1. Max is 1. In theory, sometimes it goes above that and below that in practice, but yeah. So we're going to run this, and we get a ghostly looking output for that image. Sometimes it's interesting to flicker on and off that to figure out like what is colored different ways. And you will see that clouds out in the ocean there have a low NDVI value relative to what the land is. In reality, even though it can go from -1 to +1, it's kind of, in practice, it's a little bit more constrained. So I'm going to go back down to 0 to about 0.7 for NDVI. And then that will make things jump out a little bit stronger. There are the variations. But both clouds and shadows and water, they all have low NDVI values. So NDVI can be kind of a neat way to find data that is not contaminated by the clouds and shadows as well. Okay, so at this point we have 3 lines of code that allows us to calculate NDVI on a particular image. This is such a common pattern that we have an alternative way to do it, which is just say image times a function called normalize, and I'm going to use my control space to populate the rest of it, normalize difference, and to pass into that the bands that you want to use for the normalization, B5, which is near infrared, normalized by B4. And then I'm going to go back and comment out my 3 lines before and run this again just to make sure that I'm getting something that looks pretty similar to it. So it looks pretty much the same. It should be exactly the same. Once again, it's just a really common pattern that we use to do this calculation of normalized difference for vegetation, and there's all kinds of other normalized difference indices as well. Any questions on that? Has this brought back any memories? Okay, so that is, if we wanted to just compute it and apply it to one image. But often what we want to do is apply this type of calculation to a larger image. And in order to set ourselves up for doing that, we're going to rewrite this as a function. So for right now, I'm going to say var function called add NDVI. And that variable is going to equal a function that's going to take a image as an input. And then I'm going to have this open and close parentheses to define what happens when I call add NDVI image. The first thing I want to do is calculate NDVI, so I'm going to move my little command here back into my function. So it's going to first internally calculate something called NDVI as a variable, lowercase. And then I want to go ahead and return some of this information. I'm going to return the original image, and then I'm going to add bands to it. And the bands that I'm going to add is the band called NDVI, or sorry, the image called NDVI. And so far, this has basically defined a function, but hasn't said what to do with the function. So if we want to, we can, outside of here, we can still say var, trying to get and not name everything the same way, ndvi zzz, because this is going to be temporary. And we're going to say, we call the add ndvi function and pass it in this guy called image. All right, so if you're not used to programming with functions, this might be a little bit confusing because a lot of the names are similar. So I can actually even try to clarify that later, or a little bit. I'm going to call for my function img for the input image. So now that everything should be named sort of a little bit differently. So basically, we defined a function here that takes the original image, adds in an NDVI band, and then down here, we're actually calling the function, passing in the first image of our collection. And then as final, we're going to display, display that image. And if I run this again, it should look somewhat similar, but it did not look exactly similar. That's a good question. Oh, yep, and that is because of the default way that map add layer works. If I do use the inspector down on what I added to the map, I'm going to go look down, and my NDVI image no longer is a single band. It's band 1 through band 11 BQA, all of them from the original image. And then finally, there's a band called ND. And that's not necessarily what I wanted it to be called, but that's the default of normalized difference, is that it produces a band called ND. If I don't like that naming convention, I can rename it. So I might do something like .rename NDVI for the name. Run it again. Inspect it again. And then this time it's called lowercase ndvi right there. But the reason that it's looking differently is that by default, map add layer grabbed bands 1, 2, and 3 and displayed them up on the screen. And so if I really want it to look like I had before, I can add a visualization parameter called bands, once again. And within bands, we specify a single band called NDVI. And now it's starting to look a little bit more ghostly again, how it looked before. Okay, so I realize that the naming gets a little tricky in here because we have variables inside the functions and we have ones outside the functions, and some of these I'm going to delete pretty soon because they were just to demonstrate that we can apply this to an image before we go back and we apply it to an entire collection. But that being said, any questions? Okay, if not, then we're going to take this function that we now works on a single image, and that's often the way that I'll test out functions, is get them to work on a single image. And now we're going to want to apply that to an entire collection. So I can say var, in this case I'm going to call it with underscore ndvi, just so we get a new variable name. And we will, let's see, what's our name of our collection? It's called filtered. And we are going to use a method called map. And what we pass into map is the name of the function. What I don't need anymore is that line that extracted out a single image, because now we're using the entire collection. And then also that last line where I'm displaying the NDVI, I want to display the collection that has the whole NDVI added to it. So I had to do a few updates in here. The main one was calling map as a method of the image collection filtered, and then down at the bottom updating what I'm displaying on the map. This map, once again, is a confusing thing often, because this is not map in the sense of displaying it on a map like you might talk with geospatial data. This is the mathematical or computer science definition of map something across a collection. So basically, you have something, you have a set, and you have something that you want to apply to every element in the set, and that's known as a map. So we are mapping images. We are mapping functions across images. So we have to deal with it because we're bringing together many different concepts from like computer science and remote sensing.
Why did you have to comment out the first image selector thing that you did?
Oh, the first image selector, I didn't actually have to comment it out. I'm just not using it anymore. So probably be better for me even to delete it at this point.
Like the other thing works for that.
Yeah, so let me run and see if it works. Image is not defined. Okay, so where do I still have image?
Undo.
Oh, yeah, there we go. Thank you. So, yeah, I can't do that anymore. So we have to apply the same RGB visualization parameters, which extract out the true color images. And let's try running that. Cool. All right, so that seems to have produced the exact same results. So why did we do this? It's because we no longer have to filter bounds by geometry. So I can delete that part of my code and run it again. And now it's going to apply everywhere that we have these images. So now we are presumably calculating NDVI for all of the images across the United States for a period of 3 months and getting results back on the order of 5-10 seconds at the most. This, I don't know how many images this is right now. If we wanted to, we could start figuring out exactly how many it is, but it's hundreds to 1,000 maybe, something like that. You see it appear in tiles because that's sort of how Earth Engine works on the back end. It like runs each tile that the browser or this map API in the browser is requesting one at a time, and that gets farmed out to different machines, so they all get returned at different times. This is a really noisy thing because we are by default looking at the last one that was being returned. So let's change that to the median. So once again, we're going to stop using the default reducer, which is mosaic, last on top, and basically take the median of a stack of values. And we'll run that one as well. Actually, at this scale, it's probably hard to tell much of what's going on, so let's go back to the Central Valley. It's not only clear what's going on, it's faster because we don't have to load as many of the individual Landsat scenes. Okay, so that is how you map a function over a collection of images. Any questions on that? Oh, see the code? Sorry. Yep, I hid that a little bit.
Could you color the map the same way that you did like with the single band layer? I'm just thinking like if you wanted to do it like green as high NDVI and brown as low.
Yeah, so I'm a little bit limited in what names I can use because it's these CSS colors, but I think both brown and green would be in there. So did you say brown for low?
Sure.
Brown to green. I don't know exactly which green we're going to get out of there. Oops, hit the wrong button. Run. That doesn't look very brown. Looks very red to me. If you found the appropriate color, you could. In addition to saying it like brown, you can specify RGB pairs. So I have no idea what the one for brown is, but you could do something like FF00FF, and that gets interpreted by Earth Engine as well. That was purple. Okay. All right. Something a little bit more pleasing. Maybe do black to green. Looks very dark. Black to light green. All right. Okay. So one thing that's kind of interesting that we can do when we have a collection added to the screen is that we can use the inspector to look at it. Now note that I'm actually right now adding images to the screen because I have, or to the map below, because I have called median. But if I go back and I remove median from both of these, then I'm basically adding a collection to the map. And I can use the inspector to click on that collection and start looking at actual values and also variations in the values. Now, looking at this, it's not the most useful because a lot of it seems to be flatline, because that is, it's looking at all of the bands and trying to get them on a single graph. But if I went instead, and there's one band in there in particular, it's called the QA band, which has really high values, so it distorts the entire graph. But if I wanted to do something like select out, you can put in patterns into the selection as well. So I'm going to do bands 2 through 5 as a pattern. So it's going to select just bands that fit into this. It's called a regular expression pattern. But what it allows me to do is only select out a few of those bands, and then when I use the inspector, it now starts showing you the variations in time for those bands that wherever I clicked out. And this is useful to do in the inspector, but it's also useful to do kind of as part of your script as well too. So that's the next thing that we're going to do, is we're going to produce a chart of this type of variation over time within there. But just wanted to point out a little bit, as if you are starting to work with temporal data, your inspector over there is definitely your friend for trying to figure out variations and why things are occurring the way they are. So anyway, that's under pixels, series, and you can change the representation from either a list of images to a chart that shows the variation in time. All right, but let's do that in code instead. So I'm going to go back out here and add one more line at the bottom. Get my cursor back. We're going to print out a chart, and it's UI. So what if I go into my documentation right away, there's a UI, which is user interface objects, and within there's a UI chart. So some prepackaged ways to display charts of Earth Engine data. And there's a whole section in the documentation as well on like how to utilize this. But we're going to just show one example. So UI chart.image, and then what we do to pass into that is we're going to put in our series of width NDVI. And for now, I'm just going to select out a single band, NDVI. And the other parameter that it takes with it is where do you want this information for the chart to come from, and so we're going to pass in a geometry there as well. So I'm going to run that. And actually, to make this a little bit easier, I will break this statement over multiple lines so you can actually see how it's being composed together. Oh, nope. I must have spelled something wrong there. Or I missed one part of it. So under UI chart, image, there's different types of these images, and one of them that I was trying to demonstrate in here but failed to is series. So series. and that's going to display a chart over there on the top. If you wanted to, you could change it to, once again, band 2 through 5 if you're more interested in seeing those variations over on the side. Something like that. These charts, when you print them to the console, there's a little icon that allows you to pop them out. And so it brings up a whole new browser window if you want to look at variations along there, or export it as a PNG that you can put into a publication, something like that. Let me back up a little bit to get to NDVI there. Okay, so the other thing that's kind of nice, this is a very short period of time, so maybe if we went back and did all of 2016, 01, 01 to 2017, it'd be a little bit more interesting in terms of variations. Yeah, okay, so now we're starting to get more variations in there. If we're looking at something like NDVI here, whenever you have a peak where it goes dramatically up, all of a sudden, that's probably going to be some type of cloud type of contamination. But sometimes you can see more regular patterns where it might be like intensive cropping, that they build, grow some alfalfa and then cut it down. It varies on terms of what you're trying to interpret out of there. But anyway, I just wanted to show that as a single chart. There's a whole kind of example section of UI charts that if you go into our scripts and down here under examples, there is a whole section on charts. But it's just another different way to kind of output the data. How are we doing on time? 20 minutes. Probably not great. No, we're doing a lot better than we were there earlier. All right. Any questions there? The next thing we're going to go over is doing another more complex reduction in time for creating a cleaner image. Yep. Sorry? How am I going to provide access to? Oh, the recording. I think they're just going to post it later. I don't know how long it's going to take for them to put up on the site. But we tend to collect a lot of the slide decks and the recordings, and then whichever ones that we've recorded, we just link to the Summit website. So it'll be available there. I don't know what the time frame is, though. And then also, you'll be able to go in at any time and get access to the script link just based on the presentation that you have access to right now. Okay, so I'm going to now clean up a little bit, get rid of printing my chart at the bottom. And we're going to go and build what's known as a greenest pixel mosaic. And that is to say that when there are, oh, sorry, I misspoke a little bit earlier there. The high NDVI values are actually the ones that you expect to be cloud-free. It's the low ones down here where there's probably some cloud contamination or shadows or something like that. So what is often useful to do is to take a interval of time and look for the area where the NDVI was the most intense, and that is probably one of your cleanest images. And so what you can do is actually look for where the NDVI is the highest in a whole series of time, and for that image where it's the highest, select all of the rest of the bands and use those as your image. So it's called a greenest pixel reduction by basically saying we're looking for high NDVI, greenest, and then we're going to use that as a way to select all the rest of the bands that come along with that NDVI value. So we've already built kind of what we need in order to do that. We have an image collection where all the images have the original bands, and they have an NDVI band as well that we computed on top of it. So now we're going to go through and make use of that. So right after the with NDVI, I'm going to create a new one called greenest. And this is going to start with the with NDVI, and it's going to use a reducer called quality mosaic, which I'll try to describe in words, and then you might have to look at the other documentations on it. We're going to pass in something, the band, which is going to represent the highest quality pixel. And that's what we're saying is the band, we'll look at the NDVI band, and where the highest value is that over time, use that pixel in all the rest of the bands. So basically we're using NDVI as our selector of all across all the different bands, and wherever it's the highest, use that one. So that's our greenest quality mosaic, and let's put one down here at the bottom. So I'm going to say this is greenest, and true color for greenest. And at this point, I don't really need that last NDVI one, so I'll just comment it out. Okay, so I'm going to have two layers here. One of them is, what do I want to do here? I want to compare a median reduction with our greenest reduction. I guess those are the two that we'll do. All right, so let me go find some area where it's kind of cloudy. No, that's water. All right, well, let's go to South America. There's always clouds there. The world is slow at the moment. Interesting. All right. It's kind of funny. It's like whenever you need clouds, they're hard to get to. Oh, there it went. It's starting to load. Is anybody else's response going a little slow at the moment?
Yeah.
Okay. All right, so we're going to zoom back into Georgetown in Guyana. Let's remind ourselves we are looking at 1 year's worth of data. This is the true color representation, which is being reduced by the median reducer. So the median value over that year, pretty cloudy. If we pick out the greenest one of all that time, this is the resulting image. So pretty dramatic improvement over land. Note that it does strange things over water because you know, basically it's going to have a low NDVI value over water, so it's probably going to pick up some clouds and stuff. So it works good over land, not over water. Once again, that's usually fine with any of these methods. There's areas that it works well at and other areas that it will not work as well. But that is how you use that quality mosaic. You basically create a band which you want to use for ordering, which you think designates in some way the highest quality information that you have. And then you designate that band when you're doing the reduction to use in terms of ordering the rest of the images.
But you're still plotting all the images. It's just that you're ordering them that way, right? By greenest? Like
Yeah, you can think of it as that for at any pixel, it has taken all of the images, all the pixel information there, and then for each image, it says, hey, what's the NDVI value here, 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 and it uses that for shuffling. And then it's whatever is the highest NDVI value is being what's being displayed. But the nice thing is that it's shifting all of the different bands associated with that NDVI value at the same time. So if you do want to calculate something like the normalized difference vegetation index or water index, it is actually from data that was taken at the exact same image. It's not mixing images across bands. All right. Any questions on that? Yep. The difference between quality mosaic and mosaic. If we just did a reduction of mosaic, This is our default reducer, and that just means take the last thing that it takes an entire stack of images and says, squish them all, give me whatever was on top. So it's like whatever the last piece of data was that was collected. So that is what it looks like. It's usually, especially in a cloudy area, it's like whatever the last image looks like. So it's very different. Even though the names are very similar, it's doing very different operations on it. The quality mosaic is searching through for a particular, using a particular quality metric to pull out pixels that match that quality metric that you specified. So very different. Yep.
Question about function. So I was trying to understand. In your function, you have two bands. But later, when you add layer, you select several bands from 2 to 5. So how you deal with these things?
Oh, sure. Okay, so there's a few different things going on with bands, so let me try to walk through that. Within the function, it is calculating a single band image called NDVI by taking the multi-band image, IMG, and calling normalized difference on it, comparing two bands. So that's a single band image, NDVI. And then here we're adding it to the original image. So now we're up to like 14 or so bands in that image. But when we come down here, this is, once we use that image collection, we want to select a set of bands out of there. In this case, I selected 4 bands, 2, 3, 4, and 5. And I'm going to take median value of that. But the only ones I'm displaying are controlled by this constant RGB viz. So that is bands 4, 3, and 2. The reason I did that is I might want to change this visualization to include the near-infrared band. So that's why I actually did select 4 of them in here. The other reason I did that is because I wanted them to appear on the chart when I displayed the chart. So there's a few different ways that bands are being selected as we go through here. You start off with like all the bands, you add an additional band here, then I select it down to 4 bands for the purposes of display, and then I even further narrow it down to 3 bands when I'm actually defining exactly what appears on the screen. This would work just the same if I would select the actual, the actual 3 bands that I wanted to use for output. So, yeah, I definitely am mixing. There's a lot of steps that you can use for selecting bands that are kind of all mashed in there. Okay, let's see. There's one thing I wanted to do is to go and talk about resolution of the data. And in order to do that, I'm going to go back to, where should I go to? I guess the Grand Canyon again. I'm going to go down until we can start seeing some pixelation of the Grand Canyon. And we're using Landsat data. This has, for most of the bands, it's a 30-meter resolution. It kind of varies. There's a pan band that is higher resolution, and then there's thermal bands that are lower resolution. But most of the bands are 30 meters. There is also, I wanted to bring in here the idea of the Sentinel-2 data set. So Sentinel-2 multispectral instrument. I'm going to import that up at the top, and I will call that S2. And then I'm just going to do a little bit of tweaks to my script to make it appropriate for this Sentinel-2. And one of them is if we have, I'm trying to remember what the other band was. Well, I'm going to start with the same bands there. I think, though, it was band 8 that was near infrared. So let me look that up quick because I don't have it at the top of my memory. So near infrared is band 8. Yeah, that was what I was searching for. So it's not band 5 in Sentinel-2. It's band 8. So if I go done here, I'm going to change my NDVI here to be band 8, right there. And then the other things I want to do, think of what else I have to do here. When I'm filtering the data, I'm going to change that variable from L8 to S2. And let me see if there's anything else I need to do to swap it out. Whoop, that's pretty white. Okay, and then the other thing that we have is that Sentinel scales their data differently. So if I do use the inspector here and look over on the side, they are on the scale of, like thousands. And it's basically that they don't use the same scaling for the topmosphere reflectance. But instead of something that goes from like 0 to 0.2, I could do the equivalent, sort of go from 0 to 2,000, just because they use a different scale for their the way they distribute the data. So I'm going to run that one more time. And now it's kind of, you have to go back, try to remember what you were looking at a few minutes ago, but the resolution now is about 10 meters. So, increase of 3 in both the X and Y. It's pretty much an order of magnitude increase in the spatial resolution going there. But the neat thing about this is that there wasn't all that much I needed to change. I needed to update the bands that I was going to use, potentially, because they change between the different sensors. And then I had to do a little bit in terms of the maximum value for what was being displayed. NDVI works largely the same other than changing the band names. But I now have switched to a totally different input set, from a different provider. And you could do that in a minute or so. So just the ability to switch in data sets for another one is a big power of Earth Engine. You can see a lot of examples of, like, maybe I want to use both Landsat and Sentinel and actually do a comparison or something very quickly, and that'd be something fairly simple to gen up as well with the script. But anyway, that is moving from Landsat to Sentinel-2 data. All right, what else did I want to show you? All right, I think we're gonna, okay. This next one we're gonna not type since we have 5 minutes left. The next one is how do you export data? I'm gonna jump all the way to script 14 here. And the thing I wanna highlight here is lines towards the bottom, 17 through 21. Let me make that a little larger so we can just see the new parts. Is that in order to export data, we can basically build a 3-band like RGB image, like red, green, blue. And in order to do that from a multiband image, you can call visualize. And visualize basically will apply those same visualization parameters that we've been using to display images, but calculate a new image using those visualization parameters. So if I now run this command and look at this layer called RGB greenest pixel, and I'm going to use the inspector to do that. My band names are now called VisRed, VisGreen, VisBlue. It basically has taken all of the other band information and just renamed it as these visualization bands. But that is useful because that's what we generally want to export if we're going to make like a PNG or a GeoTIFF and have it be something that we can actually see without using other software to interpret it. So I've created this 8-bit RGB image using Visualize, displayed it on the map so I can actually get like a preview, and then what I can do now is export it. And by default, it's going to export whatever area I'm looking at. So maybe we'll go to Las Vegas here. And the export is something that is not run just in time. It's one of these batch tasks. So you might export, once again, all of Africa at 30 meters or something like that. But I then can, since there's an export command in here, it allows me to kick off a task, which you can give a name. well, we'll just leave it at greenest pixel. You specify a resolution scale that you want to output at, and then you have a couple of different destinations for where you're going to dump this data. If you're just doing a single image, it's often convenient to put it on Google Drive. If you're going to do this for thousands of images, you probably want to use something like cloud storage if you're going to automate this. But also, if you've done something that's really complex in terms of an algorithm, you might want to export it back to Earth Engine as a new asset. So you're basically saving that as a static asset back in Earth Engine. And you have, by default, 250 gigs of storage to do that, whether you're uploading new images or you're creating them via scripts in Earth Engine. So for right here, I'm going to just say EE exports and hit run. And what this does now is it kicks off a task that runs in the background. And what you're going to do is want to come back later on this. And so I'm going to skip ahead to the other scripts because it'd probably be pretty fast. For something like this, it's going to be under a minute. But other ones, it'll be hours to days, depending on what you're trying to do. But while we're waiting, I wanted to just do a little bit of show and tell here with number 15 script. And this is showing a little bit of a preview of what you can do with user interface elements. And if you're interested in this script and the next one, there is a class that's, I can't remember whether it's tomorrow. Do you remember, Renee? On Wednesday? That you will learn all about the user interface aspects of the code editor. But I just wanted to show a little bit about what could be done. I am now comparing two of these images with like a slider. So you can kind of control back and forth. You know, the median composite's over on the left-hand side. The greenest pixel composite is over on the right-hand side. And you can zoom around basically and do a comparison of some sort. So that is number 15. And it took, we're up to now about 43 lines of code with a bunch of comments in there trying to explain what is being done there to get that split map. If you want to go even a little bit more complex, I added to that a ability to click on it and get a chart for wherever you click. Now we're up to about 80 lines of code. Let me run that one. Whoops. Once again, my Earth has disappeared. Come on, Earth.
Maybe it's just you, Earth.
I'll get a drink of water and we'll wait for Earth to appear.
Are there any people working on object detection or change detection using Earth Engine?
Yes and yes.
Can you give some examples?
So there is a whole course, I think it's a video recording in our documentation on change detection. By pixel to pixel change detection, it's pretty straightforward. The object detection we have in our documentation, what is known as supervised and unsupervised classifications. So you'll probably want to look in there. There is a very good talk from the user summit about 2 months ago on image segmentation. That gives you an overview of all the different methods that we have in there.
So would we be able to upload image chips or define objects? How could we provide training data to the Earth Engine?
It varies, and it's a little bit early on. I guess the stuff I was talking about is you take an image and then you figure out the segments within it. It sounds like you are more find a match for a chip that you're uploading. There was also a talk at the user summit on TensorFlow, and one of the examples in there was finding cars. And so that I think is a little bit closer to what you'd want to look into. It's pretty early on at this point, our experiments with that and the documentation that we have. But there's at least some information out there. If you talk to me afterwards, I can point you to a few of the Earth Engine engineers that are working on that too that are here. Okay, we might have to say goodbye to the Earth for a second here. I'm going to go back to my slides anyway since we're right at the end.
Do you have the codes to perform the geometric correction?
Do I have the codes from the
Perform the geometric correction.
geometric correction? if I'm understanding what you're saying, then no, that is the geometric connection that USGS does for Landsat or ESA does for Sentinel is done before we bring it into Earth Engine. There are some tools within Earth Engine will allow you to shift things around that you could do on individual images, but in general, we rely on the upstream data provider to orthorectify, train correct their images before we bring them in to Earth Engine. If you're really curious, I mean, the USGS processing is on a GitHub repository. You can actually see all their code, what they do, but it is kind of a long processing chain that they use to prepare the images. I'm not, if I didn't answer your question, come track me down after this as well. All right. The last thing I wanted to show is just like, where do you go next after this? This is just an introduction. You know, I got through some of the scripts, so you can come back and revisit those scripts. But in addition, you now have 3 days where there's at least 5, I think, more sessions of Earth Engine where you can kind of pick and choose the topics. In addition, there is a really active kind of help resources that we have. There's a developers list. There's stuff on GIS Stack Exchange where people ask questions. The developers group, I would encourage you really to join in, because it's more of like a free-form conversation on like what's being done in Earth Engine. So that can give you a good idea of what others in the community are working on. And then finally, there's quite a few videos and slide decks that just came from our recent Earth Engine User Summit that are posted online. And so that's the last link there. So those are some of the main resources. I guess one that I pointed out earlier is just the whole kind of user help, or the help guide. Sorry, I'm not even saying that right. If you go into the code editor and you go into the help menu, there is a user guide. And there is even, you know, a getting started page on there that you can start off with, which guides you through like what tutorials do you want to do and how do you start with Earth Engine. It gets you started, but then you have to decide exactly like what you need out of Earth Engine, because it's a very broad kind of platform right now with a lot of different use cases on there. So with that, I will say that we've got through 101. Thanks for staying with me. All right.